Hello everyone, I am Karan Mashru. Welcome to this video. In this video, we are going to discuss solution of the problem of the day, that is mother vertex. First of all, let us start by understanding the question. What does question say? It says that given a directed graph, find a mother vertex in the graph if present. So what is a directed graph? A directed graph is a graph in which the edges have a direction. So if we have a directed edge from node A to node B, I can only move from A to B. I cannot consider that edge to move from B to A. Okay. Then what is a mother vertex? A mother vertex is a vertex through which we can reach all the other vertices of the graph. So from one vertex, if we have a path to all the other vertices in the graph, a directed path, then we can say that vertex is a mother vertex because we can visit all the other vertices starting from that vertex. Okay. So that is a mother vertex. So if we look at an example for better understanding, here we have 5 nodes and 5 edges and the output is 0. So 0 is the mother vertex. So from 0 we will have a path to all the other vertices. So from 0 I can go to 3, from 0 I can go to 4, from 0 I can go to 2, and from 0 I can go to 1. So from 0 there is a path to all the other vertices. Do we have a path from 3 to all the other vertices? No. From 3 I can go to 4, but I cannot go anywhere. So 3 is not a mother vertex. So 0 is a mother vertex. Let us look at another example. Here there is no mother vertex. Why? Because from 0 I can go to 1, but I cannot go to 2. From 2 I can go to 1, but I cannot go to 0. From 1 I cannot go to 0 and 2 as well. Okay. So the output is -1. Okay. Our task is to complete the function find mother vertex, which takes v denoting the number of vertices and adjacency list as input parameters. So adjacency list is used to store the edges and returns the vertex through which we can traverse all the other vertices of the graph. If there is more than one possible node, then return the node with minimum value. If not possible, then return -1. So basically, if more than one mother vertices are possible, then we need to return the node which has the minimum value. Here we have nodes numbered from 0 to capital V -1, where capital V is the total number of vertices. And if not possible, there is no mother vertex, then we will return -1. Expected time complexity is big of V plus E, and expected space complexity is big of V. And the constraints are given here. So now if we think about solving this problem, first of all, if we look at this example, then here we have 7 number of vertices and some edges are given. Do we have a mother vertex here? Yes, 6 is the mother vertex here. Why? Because from 6 we can reach to all the other vertices. From 6 I can go to 1, I can go to 2, I can go to 5, from I can go to 3 from 6 as well, I can go to 4, and I can also go to 0. Okay, so 6 is the mother vertex. Okay, now how can we solve this problem? See, one brute force approach can be from all the starting from each vertex from 0 to v minus 1, apply a DFS, and in each DFS maintain a count of how many vertexes we were able to visit during that DFS. If for any DFS, if we were able to visit all the V vertexes, then that would be the mother vertex because we were able to visit all the vertexes. So what we can do is, first of all, starting with vertex 0, call a DFS, note down how many vertexes we were able to visit. Suppose it is V0. From 1, call a DFS and note down the number of vertices we were able to visit. Suppose it is V1. From 2, call a DFS, and suppose the number of vertices we were able to visit is V2. Similarly, for ith vertex, call a DFS starting from ith vertex, number of vertices we were able to visit in this DFS is Vi, and so on. For V minus 1th vertex, starting with this vertex, call a DFS, and suppose the number of nodes which we were able to visit is V of V minus 1. Okay, suppose. So now understand this. If any of this becomes equals to V, so if Vi equals to capital V, then I can say that ith vertex is a mother vertex because from there I was able to visit all the other vertices. If Vi is equals to V, what does that mean? It means that starting with that vertex we were able to visit all the vertices. So that's a mother vertex. But the problem here is of time complexity. What would be the time complexity? See, one DFS takes time of V plus E, where V is the number of vertices and E is the number of edges. Here I am applying V number of DFS. Okay, so the time complexity would be big of V plus E into V. Okay, which is not efficient. Here the expected time complexity was big of V plus E, so we need to think of something efficient. Now, if we think of something efficient, so first of all, let me tell you the approach of how we will solve this problem, and then I'll tell you the proof of how it works. Okay. So what we will basically do is, starting from vertex 0, we will call DFS. Okay. and we will cover the component which can be visited from that vertex and which was not visited before. Okay, and during the backtrack we will store the vertex number in a stack. So for example, I'll starting with 0. First of all of them are not visited. Okay, this is visited array, I have marked as false. I'll start with 0. From 0 can I go anywhere? No. So I'll push it in the stack. Okay, this is the stack I have taken. Then I'll go to 1. From 1 can I go anywhere? No. Also I'll mark 0 as visited, I'll mark 1 as visited, and I'll push 1 in the stack. Then I'll start from 2. Can I go? I'll apply a DFS basically from 2. But from 2 I cannot go anywhere further. So only this node will be counted. It will be marked as visited and 2 will be pushed. Then from 3 I can go to 4 as well as I can go to 5. And I can also go to 0, from 3 to 4 and 4 to 0. But 0 is already visited. So I'll not visit it. I'll only visit the nodes which are not visited yet. So what will basically happen is from 3 I have a node to 4, I have a edge to 4 and I have a edge to 5. Okay, so from 3 I'll call a DFS, it will go to 4. Now I cannot go further from 4, so I will backtrack. During backtracking I'll add this node in the stack. Okay, for all of this, when I called DFS for 0, at that time also during backtrack I added it here, but since it was only one element, so at that time I was not able to make my point. Now here understand this, starting from 3 is not visited yet, I'll call DFS. From 3 I'll go to 4. From 4 I cannot go further, so during backtracking I'll add 4 in my stack. Okay, also 3 and 4 would be marked as visited. Then from 3 I'll go to 5. From 5 I cannot go further, so while backtracking to 3 I'll add 5 in the stack. So during the backtracking stage we will add that vertex. Okay, so now again I cannot go anywhere further also, so now I'll also again go back to the main function from 3. So during backtracking I'll add 3 also to the stack. Now I started with I equal to 0, so 0, 1 and 2 is finished. Then I was equals to 3, but when I started with node number 3, 4 and 5 are also visited. So now we will not go to 4 and 5 because those are visited. We will go to node 6 and start a DFS from here. Now from 6 I can go to all the other vertices, but all of them are visited. Okay, this is also marked as visited. So all of them are visited. So from 6 I will not be able to go anywhere. Okay, I cannot go further because all the other vertices are visited. So what I'll do, I'll come back, I'll call a DFS of 6. But I cannot go further, so I'll come back to the main function, and while backtracking I'll add 6 to my stack. Okay, now if we have a mother vertex, this is the statement which I'm making. If we have a mother vertex, it will be at the top of the stack or among the top elements of the stack, otherwise it will not be present. Okay, it will not happen that the top element is not a mother vertex and center element is a stack. It will not happen that the top element is not a mother vertex and some center element is a mother vertex. That will not happen. Okay, so now what we need to do, if we have a mother vertex, it will be at the top of the stack. If we have, so now we'll simply call a DFS from the top of the stack. So we'll call another DFS starting from 6. Okay, another DFS, let's say DFS dash. Okay, and we'll make a count of number of vertices visited. Now from 6 I can visit all the vertices, so that count would return me 7. That is the total number of vertices. So starting with the top of the stack, if I call a DFS and if I am able to visit all the other vertices, then this is the mother vertex, otherwise it is not. Here we required only 2 DFS. Okay, in the first DFS we traversed through different components of the graph, different connected components. So 0 was different, 1 was different, 2 was different. Then in the next turn we visited 3, 4, 5 at once. Then we visited 6. And then from here I made a DFS and saw if the total number of vertices which can be visited is equal to capital V, then that is a mother vertex. Okay, so only 2 DFS would be used, so the time complexity would be big of V plus E. Okay, but now, so the main question is, how will it always give correct answer, right? Okay, so now we said that if a mother vertex is present, it will be at the top of the stack. Okay, so now let's prove it. See, let me make 2 columns. This is the top of the stack and this is the remaining element. Suppose top of the stack also has a mother vertex and the remaining element also has a mother vertex. Suppose top of the stack has a mother vertex but remaining element do not have a mother vertex. top of the stack is a mother vertex. Suppose top of the stack is not a mother vertex and remaining elements also do not have a mother vertex. And suppose top of the stack do not have a mother vertex, but the remaining element has one mother vertex. This can be 4 cases. Now what we are doing is, after putting all the elements in the stack, we are considering top of the element as mother vertex and checking for it whether it is mother vertex. Okay, so if the first case is covered, if we have a mother vertex at the top and also among the remaining elements, we are checking at the top. So first case is covered because we are checking if this is a mother vertex. If the top element is a mother vertex and there are no mother vertexes in the remaining elements, this case is also covered in our approach, because we are checking whether the top element is a mother vertex. We are not checking for other elements. Okay. If there is no mother vertex at the top and the remaining elements, then this case is also covered, because we are checking this is a mother vertex or not. If this is not a mother vertex, we are saying there will not be any mother vertex below also. Okay, so both of them are not mother vertex. There is no mother vertex at the top or among the remaining elements. This case is also covered in our approach. Okay, now the last case, top of the element is not a mother vertex, but there is some mother vertex among the remaining element. This case is not covered because we are only checking for the top element whether that is a mother vertex or not. Okay, so now suppose, let's say 4 is a mother vertex and 6 is not a mother vertex. So 4 is a mother vertex and 6 is not a mother vertex. Okay, suppose that is what is resembling this case. So we are taking this example. Okay, assume, don't look at this graph, suppose this is true. Okay, now if this is true, understand this, how did we fill this stack? From 0 to v minus 1 we traversed, and whenever we saw a vertex which were not visited before, we started a DFS from that vertex and marked all the vertices which were connected to it, right? And during the backtracking we pushed the elements in the stack. Now understand this, here during filling of the stack or during calling DFS on this, here we are calling from 0th vertex to 6th vertex, but we can also call in the reverse order, right? So suppose we called our DFS to fill this stack. In that calling of DFS, suppose 4 came first, and what can be the second case? 6 came first, right? So we are filling this stack at present and we are calling different DFS. So suppose 4 came first. Now if 4 came first, understand this, if 4 is a mother vertex, then 4 and 6 will be connected. Directly or indirectly 4 and 6 will be connected. We will be able to visit 6 from 4 because 4 is a mother vertex. We can visit all the other vertices from it. So what will happen? Something like this will happen. From 4, let's say we go to 5. From 5, let's say we go to 6. Suppose. So what will happen is, I'll go from 4 to 5, from 5 to 6. Now during backtracking, I'll push 6 in the stack, then I'll push 5 in the stack, and then I'll push 4 in the stack. Suppose there are these 3 elements. Suppose. So what I'm trying to tell is that 6 will be at the bottom, then 5 will come, and then somewhere at the top 4 will come. You understand this? During filling of the stack, we are calling different DFS functions on the nodes which are not visited. So in that calling, suppose we call DFS on 4 first, and other cases suppose we call DFS on 6 first. Like here we called DFS on 0 first, then we called on 1, then we called on 2, then we called on 3, and then we called on 6. But we can also start with 5, then 4, then 2. Okay, so suppose there can be 2 cases, either we start DFS on 4 was called first or DFS on 6 was called first. Okay, in this case where 4 is assumed to be mother vertex and 6 is not assumed. Now if 4 was called first, then from 4 6 would be, we would be able to visit because 4 is a mother vertex. So during backtracking, 6 would go in the stack and then 4 would come. So 6 would be at the bottom, it cannot be above 4. So 6 cannot be the top of the element of the stack, and 4 is above 6. So 4 here is not a middle element. Okay, so what I am trying to say is, from 4 all the remaining nodes would be visited because it is a mother vertex. So in the stack it will come at the top and 6 will come somewhere below. So our assumption that 4 is somewhere in between and a mother vertex is false. So this is not possible. So now if we look at the second case, when DFS on 6 will be called first, then what will happen? See, understand, there cannot be a path from 6 to 4. Okay, why? because we have assumed that 4 is a mother vertex and 6 is not a mother vertex. Now if there is a path from 6 to 4 and 4 is a mother vertex, it means that from 4 I can visit all the other vertices, and if from 6 I can go to 4, then from 6 also I can visit all the other vertices. It means that 6 became the mother vertex, but 6 is not a mother vertex, so there cannot be a path from 6 to 4, right? So from starting from 6 there cannot be a direct or indirect path to 4. It is not possible. So what will happen is, when I'll call DFS on 6, okay, so all the nodes which are connected to 6 or which we are reachable to 6, all of them will be considered and they would be added in the stack. So they would be added somewhere and 6 would come somewhere here, okay. There would be other elements as well, but now DFS on 4 is left because we applied DFS on 6 first, right? So DFS on 4 is left. Also, since 4 was not reachable from 6, so 4 is not visited. So now DFS on 4 would be called afterwards. Now whenever it would be called, 4 would come somewhere here. It would come above 6 somewhere. So again, 4 is not below 6 and 6 is not the top element. Here also we were getting the same problem. 6 cannot be the top element. 4 is coming above 6. If we assume that 4 is a mother vertex and 6 is not a mother vertex. So if we assume top of the stack element is not a mother vertex and some center element is the mother vertex, then we are not able to satisfy the condition of the stack. We are getting 4 above 6 in both these cases. So this is also not possible. So basically this case is only not possible, that top of the element of the stack is not a mother vertex and there is a mother vertex somewhere in between. Only these 3 cases are possible. Either there can be multiple mother vertexes on the top of the stack, either there can be one mother vertex on the top of the stack and remaining do not have, or there is no mother vertex at all. Okay, so just to conclude, what we will do, starting from vertex 0 to v minus 1, we will call DFS on all the components which are not visited before, and during backtracking we will add the elements in the stack, and from if there is a mother vertex, it will be on the top of the stack. So we will call another DFS from the top of the stack and see how many vertices we were able to visit. If we were able to visit all the vertices, then we will say it is a mother vertex and return it, otherwise we will return -1. Now let's look at its actual implementation. So now if we look at the actual implementation, so what I have done is I have taken one array visited which will mark whenever a node is visited during BFS, then I have taken one stack and I have taken some variables. First of all, I have marked all of the nodes as false, and what I have done is I have called DFS for the components which are not visited yet. So in our example, 0 was visited, 1 was visited and 2 was visited, but we were not able to reach 3 through these 3 vertices, so 3 was still not visited. So from 3 we visited 4 and 5. So similarly we'll traverse from 0 to v minus 1, and whenever a vertex is not visited we will call a DFS on it. Okay, so now if we look at this function, so what this DFS will do, from I we have a adjacency list, we have passed this visited array and we have passed the stack. So first of all it will mark visited of I as true, okay, that vertex is visited, and for all the elements which are in the adjacency list of I, where we can go from vertex I, if that are not visited before, then we will recursively call a DFS on those elements. Okay, and during backtracking, that is after we have called this recursion function and we are backtracking, at that time we will push the ith element in the stack. Okay, and stack I have passed it through reference so that all the values are maintained. Okay, then what we will do, so I have called a DFS and filled in the stack. Now if there is a mother vertex, it will be the top of the stack element. So I have again marked this visited as false, and I have called another function check if mother vertex DFS. So it is basically again a DFS function starting with stack.top element, and it is checking whether it is a mother vertex or not. I have passed adjacency list, I have passed visited array, and I have passed a variable c which is basically maintaining count of the vertices which we are visiting starting from this. So I have initialized c with 0. Okay, so I have called it. Okay, so this is the function. So here first of all I'll mark visited of I as true, I'll increment the count for the ith vertex, then for all the elements which are in the adjacency list of I, if they are not visited before, call this function recursively. Okay, so if the value of the c becomes capital V, that means top of the element is mother vertex, we will return it, otherwise we will return -1. Okay, one more thing, we were said that if multiple elements are mother vertexes, then the vertex with the smallest value should be our answer. Now understand this, here we are we are using this DFS, we are putting the elements in the stack, and we are starting it with vertex number 0 to v minus 1. So the smallest vertex, which is a mother vertex, whenever it will be encounter, it will put all the remaining elements in the stack, and it will place itself at the top of the stack because it is a mother vertex, so it will cover all the remaining elements. And we are pushing the elements during backtracking, so it will place itself at the top of the stack. So whenever the first mother vertex will be encountered, it will be placed at the top of the stack. Okay, and we are starting with 0 and going up till v minus 1. So the smallest value mother vertex will be placed at the top of the stack. So we will get answer as the smallest value, which is a mother vertex. Okay, so in this way we will be able to solve it. What would be the time complexity? If we look at, it would be big O of v plus e. Basically 2 DFS we are applying, so it would be v plus e. V is the number of vertices and e is the number of edges. What would be the auxiliary space required here? The auxiliary space required here is, if we look at the functions, then we are taking this visited array of size v. Are we taking anything else? No, we are taking only that, and then we are using some of the variables. We are also using a stack which will contain v number of elements. Okay, so this array, this stack, all of them would be maximum big O of v. Okay, and even for recursion functions, it can go up till maximum. The stack of the recursive functions, which stores the information about the recursive function, can have a maximum depth of v. Okay, so basically the auxiliary space will be big O of v, and this is the time complexity. Now let's submit this code. So we have solved this problem successfully. I hope you have understood the solution completely. Thank you.